Very welcome to today's very important seminar about fossil-free energy production, electricity production. It's of course a very important topic that we all feel are essential for us continuing living on this planet for a long time, and also leaving this planet to coming generations in a decent way, actually. My name is Hans Ellegren. I'm Secretary General, Ständig Sekreterare of the Royal Swedish Academy of Sciences. And I'm very glad to be able to wish you very welcome to the Academy and this hall, which is almost brand new, the Beijersalen. We ourselves, we think it's actually is beautiful. It has technology that usually allows me to stand there and speak without a mic, and still it will be heard. There is a voice lift system in the hall, but today when we record it, we need this microphone. And I'm very glad that so many of you have come here. And of course, the discussion that characterizes a seminar like this is kind of in the heart of the scientific process to discuss science. The Academy has nominated 4 main goals of its activities a couple of years ago, and that continue to be our strategic plan. 2 of these goals are to try to affect the politics for research. It is to hand out prizes. Those 2 aims we will not deal with today, but the other 2 aims today's seminar is an excellent example of. And those aims are to be a meeting place for science or for scientific discussion. And the other is to work for kind of science for policy, to have evidence-based information to the society, to politicians, to allow political decisions to be made based on scientific ground. And I think the topic of today is very, very nicely illustrating how new knowledge about electricity and thus energy production can help the society to convert to a more long-term sustainable society. So again, today's activity is a very good example of how we from the Academy want the Academy to work. I shall only end by thanking the organizers of today's seminar. It's mainly Göran Andersson, who we'll hear here later, is Lars Samuelsson and Lars Bergström. They are members of our Committee for Energy and Environment. And this was actually an initiative that started some years ago, but as we know, something came in between that doesn't allow us until now to hold this seminar. Again, very welcome. And Göran, please.
Thank you very much for those welcoming words, and also a warm welcome from my side to this first seminar in the series of 3 that we have called the Inevitable Transition to the Electrical Society. My name is Göran Andersson, and I'm a member of the class of Engineering Sciences here at this Academy. And I have also, together with colleagues, Harry Frank sitting there and Lars Samuelsson, can't be here today, put together this program. The first seminar, as we heard today, is about fossil-free electricity production, and it will be followed by 2 other seminars. The next one is on energy storage, that is on the 8th of June, and then the 3rd and final one on energy efficiency that will take place on the 7th of September. You can check out our website for more information, and you can also register there if you haven't done it already, of course. Our aim with this series is to give an overview of scientific, technological, and other issues that we think are relevant for the energy transition. And we have tried here to have both an international and a Swedish perspective. Today we have 3 interesting presentations, and each will be 35 minutes and followed by a question and answering session of 10 minutes. And there's one practical issue I have been reminded about here, and that is that you should, at least when you're not putting a question, of course, you should be quiet, because there is a recording system here, and if you're having some small talks in the benches here, that could also be recorded. So as we say in Swedish, tyst i klassen, when you're not allowed to, when you shouldn't put a question, of course. So without further ado, I think we should start with the first presentation, which will be by Dr. William Gillett, and the title is Limitations and System Requirements of Different Power Production Technologies. Unfortunately, Dr. Gillett cannot be here today, but you will soon see him on the screen here, and he will present his slides from his home in UK. Bill Gillett is a mechanical engineer with a doctorate in solar energy. He has worked as a university lecturer, an energy consultant, and for 14 years in the European Commission in Brussels, where he led a renewable energy unit. He has worked as Energy Program Director of EASAC since 2014. And if you don't know what EASAC is, it will be explained in one of the first slides of Bill's presentations. So please, Bill, we're looking forward to your presentation.
Thank you, Göran, very much. And good morning, everybody. It's very kind of you to invite me there. I'm so sorry that I cannot come. Göran and I went to Brussels 2 weeks ago. He did it very well, and I managed, despite wearing face masks and all the hygiene precautions, I managed to pick up COVID, and that's why I'm not able to join you physically today. I'm going to say a few words now about EASAC, so let me just put my screen on. Just to introduce where I'm coming from. I hope you can see the screen now. Is that working for you? Yes, okay. So as some of you will know very well, not least, of course, Christina Moberg, who I saw somewhere in the audience earlier this morning, who's our president, and Göran, who works with me on the energy team. EASAC brings together the 28 national science academies from the EU member states, Norway, Switzerland, and the UK. It's the European network for the Worldwide International Academy Partnership, IAP, which includes a similar network from Asia, Africa, and the Americas. We publish science-based evidence and analysis for policymakers. And when we publish the kind of reports you can see on the screen, they are endorsed by all the member academies, including, of course, the Royal Swedish Academy. We also ensure that all our work is peer-reviewed, and the focus of the target audience, shall we say, are the policymakers. So it's of interest to you as scientists, but its main focus is for policymakers and those people who influence the policymakers, not least, of course, the press. And all the work that EASAC produces is freely available from the EASAC website. Now, I'm going to begin by talking about the European Union's climate and energy policy framework, which has been developed over many years, of course, but most recently following the Paris Agreement in 2015. And I think this commitment to limiting global warming to less than 1.5, or if necessary, 2 degrees, is driving the main climate and policy agenda for Europe today. It was first reflected in a major strategy back in 2018, what we called a Clean Planet for All. And that set a vision for reaching climate neutrality or net zero carbon emissions by 2050. And that is still valid today. And it was brought into a regulatory framework in 2018 by the governance regulation. And I'll come back to that several times this morning, because that sets the context for what are called national climate and energy plans. And the national climate and energy plans are in the hands, of course, of the member states. And they spell out country by country how the goals to 2030 and eventually to 2050 will be delivered in their context. And it's important to remember the enormous diversity between the different European member states. It's not possible to do everything at a European level. The framework was brought into many different actions, more than 50 actions, in what has been called the European Green Deal. And that is really what is dominating the framework today. As well as a legal framework in these 50 actions, it also includes what they call a climate pact to engage with citizens. Because whatever we might think we can do at a business level, if we don't have the citizens on board, we won't have the politicians, and if we don't have the politicians, it won't work. As well as the citizens, it's important to have a regulatory framework, and the 2050 climate neutrality was brought into European law with what is called the climate law last year in June. And that also brought us, and I'll talk a bit more about this in a moment, what has been called the Fit for 55 package. And this is a whole package of revisions to the existing directives and regulations, which is currently going through the European Parliament and also, of course, through the capitals, including Stockholm, of all the member states. And it all seemed to be going quite reasonably straightforwardly until, of course, we had a few weeks ago this horrendous invasion of Ukraine, and that led to the Repower EU initiative, which brought all of Europe together to realize that we have to respond more quickly to a totally new context. And I'll come back also to that several times. So that's more or less the context of what I'm going to be talking about. When we talk about climate neutrality, it means that we need to reduce our greenhouse gas emissions. And if you look at the picture, you'll see that it's dominated by the big red part of the circle, which is the energy sector. Transport is important, agriculture is important, industry does its own things as well as consuming energy from the energy sector. But the biggest challenge across most of Europe is this big slice of 54%. Having said that, let me just say again, there is a big diversity across Europe, and Sweden is not exactly the same picture as you see here. So when you see things happening across the EU, you may see it has to be done slightly differently in your own country. Now, looking back over the last few years, back in 2007, we set up our 2020 goals for 2020. We said we needed to reduce emissions, we needed to increase renewable energy, we had to do something about energy efficiency. And also not discussed very often in some parts of Europe is the need to interconnect between the different member states. Because of this diversity, it's a good idea both commercially and scientifically, of course, as well, to have good connections between the countries. And over the last decade or so, more than a decade, we have been strengthening these headline targets across Europe. In 2014, they went up to 40% reduction in greenhouse gases. And what's happened at the end of last year with the Fit for 55 was that we committed to reducing our greenhouse gas emissions by 55% by 2030. And that has implications for more renewables, more energy efficiency, and quite early on, we realized that we had also to strengthen the interconnections. So this interconnections is the only one that has not gone up since the early switch in 2014. Maybe we come back to that again also a bit later. So I just mentioned this governance regulation. This contains a number of elements which are important to us. I mentioned already the national energy and climate plans, which are already existing, and I'll come back to the Swedish one a little bit later. They have to be reported on now every couple of years, and the European Commission produces a State of the Union report now based on those national plans. So there is a very frequent updating, reviewing, and discussion on how this is going, and this will be necessary to achieve these very challenging targets, particularly for 2030. What's quite interesting is that it's all synchronized now through the governance regulation with the Paris Agreement. And this has another important implication, which is that the three main components of our emissions as we manage them are the following. The first is what we call the emission trading system emissions. These are from power generation, but also from the energy intensive industries, mainly the big players. Then there is what we call an effort sharing regulation, which is where we all work together across Europe to reduce emissions in sectors which are more diffuse, like buildings and road transport. And the third element, which is extremely important in the Nordic countries, is the land use change and forestry emissions, which have been really very much strengthened in the last 3 or 4 years in terms of understanding, but also bringing them in under the governance regulation, so that there is now an exchange possible between these three elements. And that's quite crucial, because when you're generating power, traditionally you burn coal and you have emissions that have to be reduced under the emission trading system. One of the things that some countries have done is to burn wood instead of coal. And the convention is that the emission trading system emissions from burning wood are zero. And some of the industries thought this was a great idea. By bringing this together under the governance regulation, the member state government now has to bring all three together. And when you burn wood, you have to get the wood from somewhere, you have to harvest it. And the emissions from the harvesting, instead of being recorded under the ETS, are recorded under LULUCF. So the bottom line is that you don't save any emissions when you move from coal to wood anymore. It all comes under the same thing. And that's exactly what we've been agreeing to do since the Paris Agreement. But it is having quite a positive effect, I would say, in several member states. We might want to come back to that a bit later. So I want to say a few words now about Fit for 55. As I said, it's more than 14 or so different activities or revisions to the legislation, all focusing on the minus 55% by 2030. And in there are several elements which, of course, influence the way that our power sector will operate in future. Not least the alternative fuels infrastructure, the major component on updating the emission trading system. And some of you will have seen going through legislation at the moment is what is called ETS2, which brings the building sector in. And that's quite important because in many parts of Europe, buildings are heated by gas these days. And we'll come back in a moment to see that that is going to change. What is actually likely to happen is that we will electrify a large quantity of buildings that today are not electrified. Of course, in Sweden, you're ahead of the game in this to a large extent because you've had access to very low emission electricity for many years. But for a lot of Europe, that's a big change. And that electrification will be a challenge for some countries, and they may well be wanting to come and talk to the Swedes about internet connections and sharing some of the challenges of managing that process. Because the expectation is that a lot of Europe will move to electricity from renewable sources, and the cheapest and most attractive today are wind and solar, which bring emission reductions, but challenges on the electricity grid. Of course, they both produce variable electricity, and that's a challenge for grid flexibility management. So what I've been hinting at is the energy transition, and I would like now to say a few words about that. it's basically regulated by the Treaty on the Functioning of the European Union, and that allows member states to choose their energy sources. This has been a sovereign right of member states ever since we first started with the European Union. And it means that you can choose nuclear generators or not nuclear generators. And of course, there's a big variety in public opinion across Europe on this. You can have whatever renewables you like, and you can have what thermal generators you like. That's being challenged a little bit in the light of the Ukraine invasion. We'll come back to that in a moment. I mentioned the climate law and the -55. That's forcing us to look at replacing fossil fuels with renewables as quickly as we can. And of course, speed is of the essence to meet our target of emission reductions, but it's not attractive to a business that has a lot of assets in its generation plants. So that's leading to quite a challenge for the industry. The climate law also pushes, of course, energy efficiency. Renewable heating, I mentioned buildings is a major sector. The renewable heating will probably come up. And as we say, electricity, of course. And the other dimension, which is emerging very rapidly now, is a new look at the future of hydrogen, particularly for those applications which are difficult to electrify. And I'll come back in a moment to Repower EU, but as you will have seen in the press recently, this is maybe not such a big issue for Sweden because you're not consuming so much gas, but for a lot of European countries, stopping the use of Russian gas to try to discourage President Putin from his war on Ukraine is having a massive impact on the energy sector. So when we're looking at the energy transition, energy efficiency first is the slogan that many people are shouting. We need to reduce energy demand. That's a massive and necessary step. We need to think now, particularly post Ukraine invasion, at diversification of energy sources. We need to improve our security of supply. With the push to more wind and solar, we need to look at flexibility management on the grid. And that, you mentioned, Göran, the interest in Sweden in storage. That's a major issue now. EASAC produced a report on storage in 2017, and now we need to look even more widely at storing other fuels, storing water, storing heat, and of course, this allows us then to minimize the curtailment of wind and solar electricity generation. The flexible generation is really important, and it could potentially be something that we could link to hydrogen production, because when there's excess wind, we could produce more hydrogen, in theory. The challenge, of course, is to make sure that it's a business case that works if you're not using your hydrogen electrolyzers, because the main hydrogen expectation is green electricity to electrolyze water. If you're not using them full time with a good utilization level, then your business case has problems. And then demand response is a whole sector which is evolving quite rapidly. There are now businesses coming out to manage demand together with the supplies for residential as well as industry and commerce. And we'll see, I'm sure, a growth in demand response in the years to come. And as I mentioned, interconnections are going to be increasingly important, in the hope that when the wind is blowing in one area of Europe, it's maybe not blowing quite so much in others. And if we're well connected, we can share our common renewable resources. So we all agree that the European energy system of tomorrow will look different. There will be electricity used more widely. Those electricity supplies will be carbon free as best we can get them. And the aim will be to achieve net zero by 2050. Before Christmas, we were all talking about what a fantastic opportunity this was to modernize our European economy and to create new jobs and become more competitive. Since the spring, we're now rather more worried about how we're going to manage this process. And the big new elephants in the room are security of supply, which our previous business model didn't really address. We had a energy market, a free energy market, a European energy market, but it didn't really include security of supply. And that now has to be built in to the new market structure. And we didn't expect the massive inflation in the energy costs that has occurred in the last few weeks as well, or since Christmas, basically. These two issues are now changing the agenda. So we were aware of the need to have a better integration. There was an integration strategy published in Europe. We need to look at the demand on the right-hand side here for the buildings, the transport, and the industry, and the supplies of electricity, gas, and renewables, and look at the interactions. And our policies and strategies and business models need to look at the interactions between these. I'm not going to look in detail at this picture. The message is that you can't just work on buildings or on renewable electricity. You have to look at how these things are integrated. And in the middle, you've got storage and potentially other fuel production routes. These things can no longer be looked at in isolation. And as scientists, we need to bring to the table the economics, the affordability, and the thermodynamics, because of course, not every option has an equivalent efficiency. I just give an example here from the transport sector. If you produce renewable electricity and you go through a battery to produce mechanical power, you can get something like 69% efficiency. 69% of that renewable electricity can be usefully deployed. If you go through the route of hydrogen and a fuel cell, you immediately come down to 26%. And if you decide that you want to go to liquid fuels, for example, to power aviation, you suddenly find, my goodness, we're down to 13%. And these numbers don't always jump out to politicians. It sounds wonderful that you can take renewable electricity and produce a fuel that you can put into an aeroplane. But we do have to think about the science behind it. And it's these kind of relatively simple messages that we need to make sure get seriously taken into account. Of course, it's not as simple as that. And there's a big debate today about whether Europe should be importing hydrogen from other countries where maybe the renewable electricity would be cheaper, from very sunny countries or very windy areas of Latin America. But then you've got losses in the transportation phase. You've got the risks of leakages into the atmosphere. So it's not so straightforward. So we need to look at reducing the risks of overshooting this 1.5 degrees. And that means limiting the emissions from power generation. And it's not just the operating emissions, it's the whole life cycle emissions, the embodied emissions in the technologies concerned. And we also need to look at the time frame over which the life cycle emissions really impact the atmosphere. Now, wind and solar electricity generators are great. They have rather low overall life cycle emissions and short carbon payback periods, but they do need this backup and grid flexibility management. And that's a challenge. If you look at geothermal and tidal, they have much higher embodied emissions in their construction. So that's an issue. With hydropower, it's been a wonderful thing over the last few years, but as we see more climate change, that's going to change also the amount of available hydropower, and we have to see the linkages between that. Biogas is very attractive. It will be used, I'm sure, where we cannot remove the need for a gas. There are some technologies that need high temperatures and cannot easily be electrified. But biogas, like natural gas, brings with it the risks of methane leakage, which has a very high global warming potential. So that's an issue on which we need to be focusing our attention. And last but not least, thinking of the Swedish situation, forest biomass is an attractive option for some applications, and where it's been running for years, it's well managed, but it can have very long carbon payback periods. Carbon payback periods are built into the analysis these days for the climate and energy plans at a national level. And the life cycle emissions are also important. If you look here at the worst case, the coal has the biggest life cycle emissions, but gas, which many countries have used to replace coal, is not dramatically, I mean, it's about half, on the assumption that we don't have any leakage of the natural gas. But that's a big issue, because particularly gas coming from unusual places in Russia has not been great. It's not very easy to monitor exactly how big those methane emissions are from the supplies of natural gas. And with the much bigger global warming potential of methane compared with CO2, you can quickly find that your overall life cycle emissions from a gas power generation is not that much better than the coal that you started with. So we will see, I'm sure, a push to come to the renewable options where you see much, much lower life cycle emissions. I mentioned carbon payback times just to emphasize this is a great advantage of solar and wind, and it's a great uncertainty with biomass. Some of the biomass sources with very short rotation times, like agricultural biomass, for example, the carbon payback periods are very short and very useful. But there are also forestry options which have much longer carbon payback times. And what's important is to be sure you control and manage what you're doing so that we actually tackle the real challenge, which is the 1.5 degrees, or making sure that our carbon emission savings occur during the next 5 to 10 years when we're trying to drastically reduce our emissions, the 2030 goal. A quick look then at what it means for Sweden. You guys know much more about this than I do, so I'm not going to emphasize it too much, but I just would like to highlight a few points from your National Energy and Climate Plan. Your expectations at a national level are that you will have negative emissions after 2045, and that's because of your substantial forestry contribution, the net removal through forestry, and your goals appear to make it fit together quite well on that. You still have to address your transport emissions, you still have to address your normal emissions from the conventional sectors, but you do have the benefit in Sweden of a massive contribution to negative emissions from forestry. Of course, many other countries in Europe would like to share that with you because they don't have that opportunity. And in today's world, we will have to work together to achieve a common objective. And this is where the effort sharing comes in. If you look at your split of energy and the expectation as to how it's going to work, this is the picture in your plan, dominated, of course, by bioenergy, oil, nuclear, and hydro. We'll have to see how this actually pans out. The big change is in your increase in renewable electricity production, and that's expected to come very largely from the wind sector. And that will be an interesting challenge as you move forward towards your 2030 and 2050 goals. It's important to emphasize that your climate and energy plan, like everybody else's, was produced prior to the publication of the Fit for 55, or more or less in parallel, but certainly before the invasion of Ukraine and the Repower EU. There is now a massive amount of work going on amongst all the computer modelers and the strategic thinkers, trying to work out how this is all going to work in the light of the changes necessary to respond to the invasion. Your supply is dominated by bioenergy, oil, nuclear, and hydro. That might imply some thinking as the hydro is affected by climate change, if the oil, if you're encouraged to do less of that, etc. In your case, most of your bioenergy is consumed by industries that produce it. And at the moment, as I understand it, there's no plan to change that. And as I mentioned at the beginning, the requirement to report emission trading plus effort sharing plus LULUCF is a really important context, which means that you're moving to more burning of wood, if that were a suggestion, would not change your emissions, would not reduce your emissions as some people might hope. You have the benefit that you don't have a lot of natural gas to save. Göran asked me to mention before I stop, and I'm just coming to a close now. I hope I've triggered enough thoughts in your mind to ask some challenging questions of each other. What about the taxonomy? The taxonomy was published very recently, only a couple of years ago, after 3 or 4 years of work across Europe. This is an attempt at a European level to prevent what is called greenwashing, calling things renewable or sustainable when they're not really very sustainable. The taxonomy has a focus on private sector investors, and the aim is to identify those environmentally sustainable activities that should be and can be called green and therefore support the Green Deal. The Commissioner emphasized during the press conference when this was released that this is a voluntary initiative, and the member state governments remain free to do as they wish. In June 2020, the taxonomy regulation was published with 3 types of sustainably economic activity: low carbon activities, transitional activities which would contribute to the energy transition, and enabling activities. And what happened earlier this year, back in February, was that certain nuclear and gas activities were added by delegated act to the transitional category. This was justified on the grounds that they contribute to climate change mitigation and they don't crowd out renewables. This has been now put into a strong focus again following the invasion of Ukraine, and we will have to see how this works out. What is quite interesting to me, and I bumped into a colleague from the European Investment Bank in Brussels when I was there 2 weeks ago, number of financial actors do not plan to use the taxonomy, but it is nevertheless a very interesting series of, let's say, definitions of what is and what is not somehow environmentally sustainable. What's very clear is that it's not an obligation for public funding. So governments may use it as guidance if they want to, but they don't have to follow it. What is more interesting also is that the businesses are now, under the taxonomy regulation, required to declare their activities, and this increases the transparency for investment. So this has been an important step in the whole legislative framework. It does give guidance to private sector investors, but it's not mandatory. So I must bring my presentation to a conclusion. I think I'm just about to hit the target at the end, Göran, so I'm nearly there. In summary, energy policies do need to be regularly updated, and we've had very, very visible evidence of that in the last few weeks with the Ukraine invasion. Changes occur through geopolitics, but also evolving business models. The introduction of the new digital technologies is having an impact on the way that things are working. And of course, people's attitudes evolve over time. We definitely need an integrated approach with coherent policies between the different sectors, and this is becoming more and more important. Progress reporting through the national climate and energy plans should help us to streamline our thinking and to adapt to the changing world. Those who've been on the underground trains in London may have heard the shouting as you arrive in the station saying, "Mind the gap, don't fall down between the train and this platform." This is the case also in energy policy. There is a potentially big gap between the policy ambition and what you can actually deliver in the reality on the ground. And this is very important for public confidence and public commitment. As I've said, the Russian invasion has led to a massive new focus on security of supplies and the need to diversify suppliers And that will have to be introduced now into future policy making. And the future of gas in Europe is changing rapidly. Last but not least, as your Secretary General said at the beginning, it's crucial that as scientists, the basic science be reflected in policy, and independent, objective, peer-reviewed science is really important. Of course, lots of lobby groups like to claim that they have scientific backing too, but I think one of the advantages of the science academies is that we have genuine independence and we have tools in our toolbox to be sure that we maintain that. So thank you very much for your time this morning. It's a pleasure to be with you, and I'm very sorry that I'm not with you face to face. I'll stop my screen share now, Göran.
Thank you very much, Bill, for a very comprehensive overview of the EU and other frameworks that are very important for the energy transition. And before letting questions coming in here, I would like to say that you saw on the slides here some copies of EASAC reports that have been produced during the last years, and they are all available on the EASAC homepage. So I encourage people to go there, and it's not only on energy, it's on other issues too, on environment and medicine, etc. Okay, so now I leave the floor open for questions, and you could just put a question without a microphone. So who wants to be the first to say something? Well, okay, please.
Yes, when you talk about energy, you can't just look upon the energy sector, but you have to look at the total fossil demand, and then the forest then has a dual possibility there. First, it can produce energy, but also the products that come out from the forest replaces fossil products coming from fossil base. So that it means that you can't just look at the forest as an energy sector. It has to be looked upon as a production of fossil exchange in all the products they make.
You could hear the question, Bill?
I can, and I fully endorse what is being said. It's absolutely right. EASAC produced a report, I think it was about 2016 or 17, I don't remember exactly the date, on the multidimensional aspects of forestry. And the components, even in those days, were recognized to be crucial, not least, of course, biodiversity is a major element of that. And as we saw the two COPs in the last year, climate change is part of the story, but also biodiversity is a really important part. But you may have seen also at the end of last year, the Commission produced a new communication on carbon farming. And as we look at the way forward, we have to recognize that it's really, really important to keep carbon on the ground, but we also need to employ people in the forestry industry. Some of that can be from some of the other eco-services that forestry offers, and tourism and many things. But if we can use the wood for building, construction products, for other things that will stay on the ground, many people are now looking at plastics coming from wood. The important thing is not to burn it and put the carbon straight back into the atmosphere during this crucial next decade to 2030, when if we do not reduce our carbon emissions, we're going to overshoot the 1.5 degree to 2 degree target. And the worry then is that we trigger all kinds of other problems that we cannot manage. So I fully agree with you, and I think forests have a massive role to play, and I hope that Sweden will help to lead the initiatives in this area as we all try to work together to make sure that we keep ourselves within this terribly difficult 1.5 to 2 degree global warming limit.
Okay, thank you. More questions? Yes, please. And could you please state your name and short introduction before?
Hans Stakkegaard. And my question is, you speak about nuclear being in the transition phase. Personally, I think that the transition phase will be permanent, but that's another story. Now, when we try to limit Russian gas, does Germany restart the nuclear just closed?
Okay, did you get a question?
I heard the question, and very challenging question it is too. I don't think I'm in the right position to answer a question like this. What I can tell you is that nuclear decisions, like all the decisions, as I mentioned, under the European Treaty, remain with national governments, and national governments have to listen to their citizens. And we have seen very big differences between the different member states in the position of the national governments regarding nuclear. What we do know about nuclear is that it takes a long time to build a new power station. We know that across Europe, we still do not have a satisfactory solution for nuclear wastes, despite having had a directive to which everybody agreed back in 2011. EASAC actually published a report together with the Joint Research Centre back in 2014 on the management of nuclear wastes. And I looked at that again with the JRC only a couple of years ago. And we are still, as I understand it, not in a situation where we have national plans for what to do with the wastes. So that's driving, of course, a lot of uncertainty about it. The power generation in France, which was recently it should have been opened and running a long time ago, the big Flamanville power generation is still not operating. The United Kingdom has decided they're going to risk it and try and go ahead, and we have Hinkley C being built at the moment, but it's a long, long way before that's going to be operational, maybe not even before 2030, let's see. And the prices keep going up and up and up. So I think the big discussion at the moment is lifetime extension of the existing nuclear power stations, and we might see some governments extending for a few years in the hope that that will give them time to respond to the Ukraine invasion while they get the renewables and other generation sources up and running, because they can be produced more cheaply than nuclear, which is more or less one of the most expensive, and much, much more quickly.
Okay, thank you. Yes, please.
You mentioned a very important thing here on your graphs, namely the big loss that you have when you go from green electricity to either hydrogen or even more to liquid fuel that can be used, for instance, in airplanes. Now, there is, of course, lots of efforts going on to directly produce liquid fuel from the sun, from sunlight. Now, where, in your opinion, what's the time scale for that kind of effort? Will they be possible to scale them up? And is there any concentrated EU effort to help to develop these kind of techniques?
Thank you for the question. I must confess that I'm not an expert in this. I may be wrong, but my understanding is that what we're discussing here is something which is still at the research stage, not ready for immediate deployment. And so the question will be, how long before we can get this produced at sufficient scale to be significant on the policy agenda? Maybe there's somebody in the audience who can tell us the answer to that question, but frankly speaking, I just don't know in terms of technology readiness level, where are we with these technologies? I'm pretty confident that they're being studied under the Horizon Europe research program, but I really don't know the latest technology readiness level of these options, sorry.
Okay, thank you. One more question.
Coordinator for the 2030 agenda. Thank you for an excellent overview and presentation. I just wonder, many times I believe that we are ignoring the emissions made during an investment phase, whether it be in the energy sector or in any other sector. For example, here in Sweden, it has been a huge debate on high-speed railways, and many much research has been made, and could see that the emissions during the construction phase are quite high. How do you tackle this problem, and is this a focus for you when you try to inform policymakers and so on?
Thank you. I fully agree. This is a really complex and crucial point. We haven't looked at the embodied emissions seriously on the public transport work, so I don't have any immediate pointer towards that for railways, I'm afraid. When we did our buildings decarbonisation report last year, we made a big emphasis on embodied emissions in the building sector, and we were encouraging the serious look at how you don't demolish, but you use the existing materials as much as possible, how you should be looking towards timber frame buildings, which have the twin benefits of not using cement, which is a massive carbon emission technology, and actually keeping the tree wood on the ground. That you get a double benefit if you move to timber frame buildings and the new engineered timber for structural activities. I'm sorry, I don't have data for you on the public transport for railways, but the concept is really important, and we are trying to push this as much as we can. And the table that I showed in my slides from the United Nations reports emphasizes this life cycle analysis, including not just the operating emissions, but also the embodied emissions during construction. This is really crucial. With this very short time frame before 2030, these issues are really, really important. A lot of life cycle analysis is done over 80 or 100 years. You have to do it differently when you've got a time limit before you overshoot your global warming target. And that's fundamental to the whole thinking of life cycle analysis. You're absolutely right to put your finger on this point.
Okay, thank you. I think we can entertain one more question before the coffee break, so please.
Sandvall, I'm with the Swedish National Grid. I think you outlined sort of a rapid transition, and what I hear is a lot of new assets. I mean, wind power, power lines, nuclear, hydrogen storage, and so on. And one thing we didn't talk so much about is the permitting process. I mean, to get the permits for this could easily be more than 10 years for a single asset. So I personally think this could be a big bottleneck. So I wonder, on the European level, do you see a lot of initiatives to speed up the permitting process to enable this rapid transition? So I don't think it's a question of technology only, but to get the permits to do this.
Absolutely right. Absolutely right. In the Repower EU package, there is serious discussion going on, as far as I understand it, both in the Parliament and in the Commission. And my guess is the member states must be discussing it too, though I don't have access to all of that. If we don't ease up the permitting a bit, we're going to have serious problems in delivering the 2030 goals. And unfortunately, of course, we don't want to turn Europe into some kind of new monster. We want to leave the sovereign right of national governments to manage the situation with their own citizens. And citizens have the right also to express their views in democracies. So it is a challenge, but there is certainly an effort to look at how we can somehow try to streamline as much as possible the permitting processes, particularly for the infrastructure which is necessary to facilitate the greening or the carbon emission reductions that we've been discussing. And one way of linking that, of course, is with funding coming from a common source. There is also a big push with the Social Climate Fund to support those people who are with low-income households or other struggling, who can sometimes respond in a negative way, not because they don't want to go green, but just because they want to complain about the environment in which they're having to manage with inadequate financial resources. So there are efforts being made, I think, from different perspectives to address this really important issue. Because if we can't get the infrastructure in place, we have a massive challenge. And strengthening of electricity infrastructure is traditionally a real challenge. That's one of the arguments, of course, that the gas industry lobby is using to say we have our network of gas pipes. We don't actually need to get a lot of permits to have that adapted to carry other gases. The challenge is to find enough other gases. We can't produce enough biomass. Big question mark at the moment with the Ukraine challenges that they have. What's that going to mean for the agricultural production in the other member states, which may have to go up to compensate for the lack of food being grown in Ukraine, which has been a massive food producing country for us for many years? Will that have an impact on our ability to produce biomass and therefore biogas, and therefore, of course, biomethane to put into the networks? So I think there's quite a lot of thinking and discussing going on at the moment on this crucial issue of how do we get the permitting out of the way so that the necessary steps can actually be taken. And it will be a country by country thing. And I think if the Swedish Academy can be talking about this to the Swedish government, that would surely be a constructive, useful scientific input for you guys to be giving to your national government, as indeed all the other countries must be doing as well.
Okay, thank you. And I think we have to finish this session here. And I would like to finish by a quote by the President Dwight Eisenhower of the United States. It's claimed that he said that plans are useless, but planning is essential. So I think this was a good illustration that the future will not be as we thought, but if we have plans, we can modify the plans. So the whole planning process is the important things and perhaps not the plans per se. Okay, thank you once more, Bill, for a very excellent presentation.
Thank you.
And those present, we will meet here then at 10:20, and coffee will be served outside here now. Thank you.
Thank you very much.
Thank you. Bye, Bill. Okay, thank you very much for coming back in time. So we go on then with the second lecture of today, Photovoltaics Visions, by Professor Martin Green. Martin Green is a professor at the University of New South Wales in Sydney, so he has travelled a long way to come here. And he's also the director of the Australian Centre for Advanced Photovoltaics. His group's contributions to photovoltaics are well known and include holding the record for silicon solar cell efficiency for 30 of the last 39 years, described as one of the top 10 milestones in the history of solar photovoltaics. Professor Green has a number of international awards received, include the 2002 Right Livelihood Award, the Global Energy Prize in 2018, and the 2021 Japan Prize. So, please, the floor is yours.
Well, thank you, Göran, and thank you to the Academy for the invitation to speak to you here today and for all those that made the visit possible. As Göran mentioned, I'm Martin Green from the University of New South Wales, Sydney, and down at the bottom right there, that's the Scandinavian-inspired Sydney Opera House. And middle there are our labs at the University of New South Wales, located between the city and the beaches in Sydney. And the final shot there shows our solar industrial research facility where we do technology transfer to industry. And as you'll see, we've had a lot of contact in industry in getting solar technology promoted and commercialised by that industry. The outline of my talk's very simple: past visions, present visions, and future visions. It all started with the young Edmund Becquerel, 1839, who used the apparatus shown there to show that light could be converted to electricity for the first time. So that was the start of photovoltaics. The next big step forward was Einstein with his Nobel Prize winning work, just showing that in its interaction with matter, light had to be regarded as coming in little clumps of energy that we now call photons, and that's essential to understand how a solar cell works. And that, of course, led to the development of quantum mechanics in a roundabout way. And in 1931, Alan Wilson from Cambridge solved the equations for, well, I guess semiconductors in particular, just showing in these regular crystal structures the electrons were confined to bands of energy within the material. And in a semiconductor, you've got one full band or nearly full band separated by an energy gap to the next fullest band. And that energy gap is a really important thing in photovoltaics. You can specify limiting performances on solar cells and so on just by knowing that energy band gap. A lot of progress was made in, well, the big step was made in 1941 at Bell Labs. So Russell Lowell, shown in the photo there, was investigating cat's whiskers diodes for microwave rectifiers. So you just poke a bit of metal onto a semiconductor, silicon in this case, and he was trying to improve these. So he tried to make some very pure silicon, use the best material to get a hold of. And when he cut little bits out of this ingot of silicon that he prepared or had prepared, he found that if he shone a torch on it, one side became positive and the other side became negative. And that was a big step forward, not only for photovoltaics, but for the whole of microelectronics. So he realised there was two different types of materials there, and one he called positive type, because that's the bit that went positive when he shone light on it, the other negative type, or N-type. That's the bit that went negative. And just sort of investigating, why these properties occurred, it led to the discovery of the role of impurities in the silicon in doping the silicon and giving it these different properties. The N-type has surplus electrons and the P-type has surplus vacancies or holes. But that sort of triggered the whole microelectronics revolution, and William Shockley, who won the 1956 Nobel Prize for sort of building on that understanding to design these NPN transistors. So the early transistors were like cat's whiskers type transistors with bits of metal poked onto a piece of semiconductor, germanium, but he conceived that you could use this doping to control the electronic properties within the material and form what's called an NPN transistor, shown on the blackboard there. So the side nearest William's head there is called the emitter. It emits the electrons, and then there's a P-type base region, and then there's an N-type collector region. So that terminology has carried over into photovoltaics. So we have an emitter, which is the top region of the cell, and then the base is the main region of a solar cell. So it doesn't really mean anything in the solar cell context, but that terminology is a carryover from this era. So by the middle of last century, everything was known that is known now about solar cells, essentially. So this is the diagram of a solar cell that Volker Quaschning there has drawn. But the light enters the semiconductor in little packets of energy. The photons excite carriers across the bands that Alan Wilson suggested were there, and you get transport in the upper band where the electron's excited to, and in the lower band because of the vacancies there. So you get positive and negative carriers moving through the cell, and you put a PN junction into the cell, to make all the carriers go off in the same direction. The electrons go one way, the holes go the other, and then if the circuit is completed, the electrons will flow through that circuit and join up with the holes on the other side. So after all that was understood, very rapid progress was made. So the initial efforts went into making these NPN transistors, but a result of that effort was first efficient solar cells were made in 1954. And the structure is shown there. It's what would be called an emitter wraparound cell now, in that one dope layer goes right around to the back and both contacts on the back. And there's Pearson, Chapin and Fuller who demonstrated the first cells. It made front page on the New York Times. So this is a page from April 1954. And there was all kinds of hope for a massive application of the technology. You can see the family there looking at this solar panel that's doing something wonderful. So vast power of the sun is trapped by, I'm having trouble reading it, battery using sand ingredients. So a lot of excitement. But the technology was far too expensive then to be used for anything, but fortunately in 1958 some of these cells were put up on the second US satellite, Vanguard 1, and they worked really well. Too well, in fact. They were still beeping away 6 or 9 years, I forget which, after the satellite was launched, which was a bit of a nuisance because it was sort of clogging up the radio waves. But that application was a success, and for the first communication satellite, Telstar, there was a big effort at Bell Labs again to try and get the technology, fully developed. And it was a couple of years' effort in developing the cells and testing them and so on, and ended up with a standard cell that you can see in the photo there at the front, 2 centimetre square. And when I joined the industry in the early 70s, that was called the conventional space cell. So that remained the mainstay of the industry for right through the 60s until the early 70s. Because of course you have to be quite conservative when you're launching things into space. You don't want to change things too quickly. The little chart there that you just see down the bottom left, just showing the evolution of efficiency. So Russell Ohl's devices were less than 1% efficient, and then in the 50s with this developments, mainly at Bell Labs and then some commercial companies that licensed the technology from them, the efficiency got up very quickly to close to 15% for a terrestrial cell. The cells are a little bit less efficient in space because there's more blue radiation there that the cells don't convert as efficiently as the red, as we'll talk about a little bit later on. But then in the late 60s, ComSat labs were set up to try and improve satellite technology. And one of the things they identified that they might be able to improve was solar cells. So Joseph Lindmayer, who's shown there, was given the job of trying to improve cell performance. He wasn't too happy about it initially, but he did quite a good job, and he ended up leaving ComSat a couple of years later and setting up his own company to make the cells. So he had a fresh look at the design and came up with an improved cell, first improvement for about a decade in the performance of the cells. He left to set up his company, and then the next year his team at ComSat introduced texturing of the silicon. So these early cells were made on monocrystalline wafers, and if you attack them with etchers that etch different rates in different crystallographic directions, you can expose crystallographic planes within the material. And so if you start with the right orientation, you can end up with these little pyramids, nearly exactly the same geometry as those at Giza, but just a lot smaller, all over the surface. You're a few micron sort of base length for these pyramids. And so that was called the black cell, because if light strikes the side of one of these pyramids, it gets reflected downwards. So if you get 10% reflection from there, after the second reflection, you're down to 10%, which is 1% reflection from the total device. So they looked like black velvet. They weren't too popular for space because they used to heat up more than the standard cells. because they also absorbed some of the infrared light as well as the light the cell could convert. But they became the standard for terrestrial use. So the metallization was simplified, but that cell structure shown there on the right, the aluminium back surface field cell, became the standard for the industry for the next 40 odd years, as we'll see. These pyramids are great for reducing reflection. They're wide band, so you can use anti-reflection coatings, but they're quite narrow band, whereas these are broadband reflection control processes. You've got your PN junction, and then at the rear of the cell, the aluminium was used because it is a group 3 element, and if you alloy it with the silicon, you can end up with a aluminium doped region that's heavily doped P-type material, and that protects the that reduces the electronic activity of the rear contact by having that sort of protective layer intervening there. So that structure was a very tidy structure. It encapsulated the best technology that was available at the time, and quite simple to manufacture. Also, the 70s were the era of the oil embargoes, and many countries, particularly the US and Japan and Europe, launched programs trying to develop alternative sources of energy so we weren't dependent on fossil fuels. So greenhouse wasn't as big an issue as it is now, but resource availability and so on was what probably was the real driver behind these programs. So it started in the US as Project Independence, get free of dependence on oil. But one of the main outcomes of that program was reliable packaging for the cells. So through a series of block purchases, they contracted with the industry to supply sample modules meeting various specs, and then as they tested those and found out where they were weak and where they were strong, they refined the specs and sort of guided the industry towards a design which is still used today, some 40 years later, as in 45 years later. So the encapsulation was developed around this era, and that's one of the reasons that photovoltaics has done so well. This really good encapsulation has been available from that era, thanks to the efforts largely at the Jet Propulsion Laboratory in the US. I started in the early 70s, and that's me with the long black hair there, and my first PhD student. And we didn't have much equipment, but we're using just about all of it in that photo there. But in my PhD, I'd looked at other ways of getting the same electronic activity as with these doped regions in the material. So using what would be called a heterojunction approach now. So my thesis was to look at the properties of, in microelectronics. The metal oxide semiconductor structure has been the backbone of the industry since the early 70s. So my thesis was looking at what happened then when you made the insulator layer very thin so that you got quantum mechanical tunneling through it. It normally provides electrical isolation of the metal from the semiconductor, but my thesis was looking at that, and I sort of showed that you could get all the same type of properties that you'd get from adding dopants to the material. So we were trying to show that that happened. And fortunately, we are able to get high voltages. The little curve there just shows the output curve of a cell that we were measuring with a simple lamp there. That's a very poor output curve for a solar cell, but it's quite typical of what you get generated by a cell. So if you have no voltage across the cell, short-circuit it, you can do that with a solar cell without damaging it, unlike with a conventional chemical battery. You get what's called the short-circuit current, and then if you open-circuit it, you get the open-circuit voltage, and the power output is some fraction of that product. And that parameter that makes the power equal to that is called the fill factor. So you multiply the voltage by the current and by this fill factor curve term, and you get the power output. So we weren't set up to really make good cells, but we could measure the voltage, which was quite easy to do. And fortunately, we were doing better than most in that era. And we pushed the voltage along to record levels, and then we realized we had to actually try and use those high voltages to make a high cell. So our team grew, and we made our first world record cell in 1983, an 18% efficient cell. So that was the first improvements in ComSat in 1974. And the cell structure we actually used these tunneling devices. And there's a commercial technology called TopCon that is using similar tunneling contacts now. So it was a forerunner to that technology. That same year, we realised we've been concentrating on the front of the cell, and we realised we had to fix up the back, and that's when I drew this diagram of a PERC cell, passivator, emitter, and rear cell. And I'm just mentioning that now because it's the dominant technology that's used commercially nowadays. It has a very long history though. So we kept improving the efficiency, and we made the first 20% efficient cell in 1985. And that had long been regarded as the 4-minute mile of photovoltaics. In the early days of the cells at Bell Labs and so on, people were trying to estimate what type of efficiency you could get from a cell, and people came up with this figure of 20%. That's about the best you could do. So that was the 4-minute mile, and we burst through that in 85. And there's my team. We're steadily growing due to these world records that we were setting. But like many of my students, a lot of these went on to have a big impact in the industry. So not only were we developing the technology, we were training a lot of the people that went on to play a major role in the development of the industry. Our run of records was interrupted by a group at Stanford, led by Dick Swanson, with an unusual cell structure where you put both the contacts on the same side, going back to a similar structure to the first efficient cell that I showed earlier, with both contacts on the back, although different physical principles are involved in this case. This technology has since been commercialized by SunPower, and you can see a photo of some of the cells there at the left in the inset. But from the back, you've got the cell mainly covered by metal, so that's the shiny look due to the metal on the back. But from the front, you've got no metallization, so it looks like black velvet, as I mentioned before, because of those pyramids that are along that surface. So the sunlight in this diagram is coming from the bottom. I used to always joke that coming from the southern hemisphere, the sunlight came from a different direction. It used to come from the top of the cell rather than from the bottom. But that is now a commercial cell. And in fact, the highest efficiency commercial panel you can buy now is 22.8% efficient, and that uses this technology, and it's marketed by SunPower, although it does use our tunneling contacts on the rear of it. So that spurred us on. Our record was broken, so we worked hard to get that PERC cell structure I mentioned earlier implemented, and we were quite successful. So we lost our record for 6 months, and then started regaining it, pushed on to 25% efficiency with this structure here. In Japan, work was taking a different direction. Japan had been very strong in developing amorphous silicon. So if you own a solar-powered calculator, it'll be an amorphous silicon cell that's in that. And Japan were very active in developing that technology, and it was long thought that would take over from the crystalline silicon as the dominant commercial technology, but didn't pan out that way. But there's interest in Japan in combining the two. So initially they realized that putting an interfacial layer between the two would help. Initially it was oxide, citing our earlier work. But they found that putting intrinsic layer of amorphous silicon. This amorphous silicon is deposited in a way that incorporates a lot of hydrogen, and the hydrogen is there in like 10% type of levels, and so it's an alloy of silicon and hydrogen, and its electronic properties are different from those that you'd expect from a pure amorphous silicon layer. So it's a wider band gap. So this is a heterojunction type of structure, fairly similar to the tunneling structure we were trying to implement back in the 70s. But that's the heterojunction solar cell, which was developed by Sanyo and Panasonic when they took over Sanyo. And they got to close to 25% efficiency in 2012. And just recently, one of the solar cell manufacturers in China has got 26.3% with this type of structure. So that's a really nice result. And then the record for a silicon cell is now 26.7, and that's using the SunPower type approach with the contacts all on one side, but combining it with this heterojunction type of technology. So combination of two of the stronger technologies. So that's where we are now in terms of efficiencies, but commercially there's been a big turnaround in the industry over the last 7 years or so. This just shows the share of the market of different technologies. So the blue and the maroon regions are that technology that I showed you that was developed in, basically back in 74 at ComSat Labs. That's the aluminium back surface field technology. It completely dominated the industry from the early 80s up to 2015 or so. And then the yellow and brown regions started taking over, and that's our PERC technology. So very rapidly took over, and last year accounted for 91.2% of silicon cell production. So we're very proud of that, to have seen our technology travel all the way from our lab in Australia back in the 80s to now that it's globally dominant. The really big thing that's happened, however, in photovoltaics is not so much in the development of the cell technology, but in the reduction of the costs, although the two are somewhat related. So this is just a cost chart, well, price actually, showing the average selling price. So there's market survey companies that phone around each week and find a figure for the average selling price, and this is just documenting the figures that have been published over the last 13 years. So you can divide it into 4 regions that each have their own story, but the most recent, well, I guess there's a 5th region now, which is the coronavirus region that has affected the pricing, but the region immediately before that was the region where the PERC started taking over, that transformation you saw in the previous slide. So the incumbent technology had to rapidly reduce prices to maintain market share, or to try to maintain market share, and that sort of drove prices down. So we figure prices are half of what they would be without the PERC being introduced. However, the bigger changes occurred a bit earlier, around 2008, and the gentleman shown to the left there is my 12th PhD student, Dr. Zhengrong Shi. That's not how you pronounce it in Chinese, incidentally, but despite my best efforts, I've never been able to get it right. But that's how we used to pronounce it in Australia. But he was working in our R&D company we set up, and he got getting a bit anxious about getting stuff onto the market, so he decided he wanted to set up manufacturing in China, which was pretty hopeless in the time he wanted to do that, because there was just no manufacturing there to speak of and no infrastructure for doing that, but he was determined. So he decided to set up manufacturing in China. This is 2002, the opening of his first factory, and I got to do some of the heavy lifting, cutting the ribbon. You can see me in the front there. And we just thought, oh, well, this is good fun. This is not really going to go anywhere. It's just too tough. But he got the factory going, and Germany had the feed-in tariff program that was very successful in developing the market in that era. And he was able to sell his cells onto that market. The performance was quite good because had all our team helping him set up the technology, and we were still record holders then, so we could give him better technology than just about anyone else. And a lot of our people either left us to join him as co-founders or worked for him part-time, like Stuart Wenham, shown there immediately next to Zhengrong, who was part-time CTO. But Suntech went well, was selling cells in Germany and reinvesting the profit in more manufacturing facilities, got noticed by some US investment banks, and this is why we have cheap solar cells now, in that Morgan Stanley and Goldman Sachs approached him and organised a management buyout, And he became the first private Chinese company to float on the New York Stock Exchange in 2005. And that was a huge success, the biggest technology float of that year. So Gillett started with a 6 million investment from Chinese companies, and here he's getting 400 million injected into his company only a few years later. So huge success. But that triggered a chain reaction. So Goldman Sachs made over 200 million on the launch, and Gillett raised 400 million. So there's an interest both from investment banks and Chinese potential manufacturers to get together, and that caused a rush of Chinese listings, Chinese companies in China listing on the both New York stock exchanges, NASDAQ, and the New York Stock Exchange between 2005 and 2008. And they were all huge successes. So the next ones to go were only involved in assembling modules in China, but they did very well. So Trina and Canadian Solar, so they're two of the big names in the industry now. They weren't as sophisticated as what Gillett was doing, but did well. And then there were 9 companies that listed before the global financial crisis, and 6 of those 9 are in the top 10 manufacturers now globally. So this massive investment of funds into these small manufacturers really created the modern industry. So it was over 7 billion invested through listings and debenture notes issues over that period. And because Gillett had come from our lab, all the US investment banks wanted to see some type of contact with good technology within these companies as part of their due diligence. So all my students, particularly those that could speak Chinese, although not all of them could, got gobbled up to become CTOs or whatever of these companies, or some were founders like Gillett. So we have a very good contact with the industry as a result of that. So present. PERC has done so well. That's the technology we developed, and one of the reasons is that it's easy to fabricate cells that respond to light from both directions. And I guess that photo there on the left sort of shows why that might be useful. You get a lot of stray light falling on the rear, and you can get between a 5% if you do nothing, like in this case here, nothing special is being done, or 20% if you put white pebbles down on the ground or something like that, make a bit of an effort to get more light reflected onto the rear. And also the cells are rectangular. They're fabricated on square wafers, but they're rectangular, and that's another thing that's become possible with PERC, because you have to pattern the rear of the cell, and previous technology was difficult to cut the cell down to smaller bits after fabrication, but with PERC you could do that. So that meant the wafer size that you used in manufacturing started increasing just very recently. So it was 156 millimeters square for a long time, because that generates about 10 amps of current under sunshine. So a solar cell is a large current, low voltage output device. The output voltages are related to the photon energies that are falling onto it. And the average photon energy is 1.3 EV or something like that. So you're stuck with voltages below 1 volt in general from these cells, but enormous currents. So 156 millimeter square wafer will generate about 10 amps, and you need a lot of copper to handle anything bigger. But with the PERC, you've been able to go to bigger wafers and then chop them up after you've processed them into cells. So the long time solar cell industry used smaller wafers that are used in microelectronics. So the yellow circles there just show the evolution of the size of wafers used in microelectronics, up to 12-inch now, or 300 millimeters. And the solar cells have now caught up. They're using 2 10-millimeter wafers, which is the biggest square wafer you can cut from that wafer size. This is just from the roadmap for microelectronics from around the turn of the century, but the size of wafers had been going up about 50% every 10 years. So they thought, well, that's going to continue. So by now we'd be up to a 675 millimeter wafer if it had, such as shown on the right there, massive wafer size. But the photolithography that you require for microelectronics, you're after ever finer dimensions. Doing that over ever larger areas was just too tough, and So the 300 millimeters is still the standard for microelectronics. And the latest plans to move for 450 is 2029, although that date sort of keeps getting pushed back. But solar cells not being dependent on photolithography might see the bigger wafers used. So modules have grown in size as well, as suggested by this graph here. So you're now up to about 3 square metre modules in area, so up to about 700 watts rating, the one shown on the far right there. So that gentleman is 6 foot tall, give you an idea of scale. So at the moment, the size of the module is determined by what 2 people can conveniently carry around all day, which is about 40 kilos. So that's limiting the size. But if you use mechanical equipment, you can perhaps go bigger. So perhaps the biggest size is what you can fit into a shipping container. So a shipping container, if you use the full area available, you could do a 30 square metre module. So 30 square metres or some fraction of it is probably what we'll see in the future, 3 square metres now. Okay, well, more into the future. What comes after PERC? And one thing you can do, the solar cell is just a photon converting device. One photon goes in and you get 1 electron out. So it doesn't matter if it's a blue photon that has a lot of energy, much higher than the band gap, or a red photon that, in the case of silicon, is close to the band gap energy. You still get the same outcome. So you're sort of wasting the energy of the blue photons. So one way around that is to stack cells of different band gaps on top of one another, as shown diagrammatically on the right there. So you stack the highest band gap cell uppermost, and you get this really tidy filtering of the sunlight, so that material gobbles up all the blue photons, but it's transparent to the photons that are below its band gap. It's just like an insulator, like glass, for example. They just pass through to the next cell. So you get the photons automatically steered to the material that's best able to convert them efficiently. So, really, nature helps you out enormously there. So that's a really great idea, and because the silicon industry is so large, stacking them onto silicon would be a good strategy for gaining early market entry with this type of approach. So I think that's the real challenge facing photovoltaics now, is to find material that you can stack onto silicon that has all the desirable properties of silicon. So silicon's abundant, it's non-toxic, it's stable, and it gives you good efficiency. So finding other materials that meet all those 4 criteria, I think, is the biggest research challenge facing photovoltaics right now. And if you can do that, you can increase the efficiency. So the graph on the right there, the green just shows the limiting efficiency for a single silicon cell, and then the next one over for 1 cell stacked onto silicon, and then 2 cells stacked onto silicon. So the efficiency goes up quite markedly from 29% to 47.5%. Just stacking 3 cells. If you keep going, you can double the efficiency of silicon, like with a semi-infinite number. The red just sort of shows if you had any choice of material. So if you, the green is with silicon as the bottom cell, the red is if you had any choice of material you wanted for all the cells in the stack. So silicon's a pretty good choice, not only for a single cell, but for a cell in the stack. So you can stack 2 cells on silicon without, if you stack 1 cell on silicon, 2 cells is sort of a no-brainer, but the photons are shared between these cells, so that every time you stack another cell, the contribution of the silicon cell to the overall power output reduces proportionally. So 2 cells, you get half the contribution of silicon, 3 cells, you're down to a third. So by the time you get to 4 cells, you'd say, do we really need the silicon? And you'd probably go to an all-thin film technology using these other thin film technologies that would be validated probably by terawatts of production experience by the time we got to this juncture. Okay, so I'll just finish off a little bit on the market. This just shows the growth of the wind energy installed, wind energy capacity, and solar. So the wind energy capacity has sort of grown linearly. If you look at those blue bars there, sort of a bit of a linear improvement, but the solar continues to grow exponentially. So it overtook wind in terms of total capacity a little while ago. End of last year, there was 979 gigawatts of solar installed, very close to a terawatt. and in March this year it actually exceeded 1 terawatt. So there's about 190 gigawatts, or 0.2 of a terawatt, installed last year, and with this exponential growth we should reach the 1 terawatt level of photovoltaics if it continues sometime this decade. And this just sort of shows you what 1 terawatt will do if you're displacing coal from electricity generation or oil from transport, which are the two easiest targets. This is what it'll do in terms of total CO2 emissions. 1 terawatt a year, year after year, sort of puts it on one of these trajectories that you need to restrain global temperature rise to less than 2 degrees centigrade. I really liked this chart when I saw it in 2015 because it just sort of shows the real challenge we're facing. Despite the best efforts of the 4 biggest emitters, we're going to run into our total budget pretty quickly if we don't do something quite dramatic. I'll finish off. IPCC last month reduced this report on mitigation of climate change, and they include mitigation options and costs of approaches that had immediate impact, up to 2030. And they produced this chart here, which I'll zoom in on the important bits, but the bit 2/3 down is transport. So there's a lot of blue regions there, and the blue regions are the good regions. They're things that could be introduced at 0 or negative cost. So it's sort of no-brainers. So there's a lot to do with transport. Zooming in on the top region where the most blue is, and you see solar and wind energy, you can cut back greenhouse emissions according to the IPC by several gigatons a year by immediate implementation of these technologies, and save costs at the same time. End of talk. So just somewhat of points I wanted to make. Those are just the chart there. It just sort of shows most optimistic vision for photovoltaics that's been published by Lappeenranta University of Technology in Finland in energy last year, but just sort of showing 64 terawatts of photovoltaics installed worldwide, and amounts per country. I can see Sweden is down for about 70 gigawatts of photovoltaics, so now has over 1 reached, I think, last year or the year before. So on their way to 70 terawatts. Australia has about over 200 gigawatts of photovoltaics installed in this scenario. So amazing detail of analysing all those different regions are shown there, and coming together with a energy generation and storage options for all those regions. So I like the quote that was made before, you need a plan, but whether the plan will actually look like this or not, anyone's guess. So what we're going to see photovoltaic costs continue to reduce. It's still sort of horse and buggies days to my thinking, we've still got all these tandems to introduce and so on. So we're going to see it become insanely cheap. That's a phrase Rama's Naam termed that I really like. New technology like PERC accelerates the pace of change, so it's good. All these technologies that are in the wing. We're going to see solar module prices after coronavirus impact moves through the system. We're going to see much cheaper solar panels. We've already seen electricity prices of 1 cent a kilowatt hour bid in Saudi Arabia for electricity supply. So we're going to see that become more routine over this decade. So very low electricity prices. Some people are talking about the third energy revolution that's going to be introduced by having abundant solar energy available at these prices. Over 100 times more solar resource than what we're presently using in primary energy. And solar is destined to play a major role in mitigating global warming. So thanks very much for your attention.
Thank you very much. And for this very interesting overview of future prospects. So questions from the audience, please. Yes?
Could you say something about the lifetime of these various cells, and also how lifetime could vary with climate where they are put up?
Yes, very good question. So that work that I mentioned was done in that modular encapsulation was really very good, and most manufacturers nowadays, or all manufacturers nowadays, will give you a 25-year warranty on the panels irrespective of where they're installed worldwide. And one manufacturer who I mentioned, SunPower, who happens to make the most efficient panels, also is now giving a 40-year warranty. So somewhere between 25 and 40-year warranty you'll get on the panels. And yeah, there's been plenty of field installations that were installed in the 80s and so on, and have documented that that type of life is feasible. Of course, there's many systems that haven't lasted that long, but there have been some that have shown that you know, there is some substance behind those types of figures. So in general, solar cells don't like hot, moist climates, so they're the most demanding for the cells. But you know, like in most European climates, it's regarded as quite benign for the solar systems. So increasingly, we're seeing initially a lot of the installation was in Europe because of the various feed-in tariff programs that were established early on here. But we're seeing increasingly the panels being deployed in more and more harsh environments. And you know, India has proved particularly challenging, and people have had to take real care with the product there. But the durability is improving, like the testing is becoming more rigorous and more thorough, and year by year I think the quality of the product continues to improve, you know, despite the fact that it was already very good from the 80s onwards.
More questions?
Thomas Sandvall. I mean, looking at this picture, I think in Sweden we saw a lot of rooftop installations.
Yes.
Do you think that will be dominant, or are we looking at large gigawatt scale power plants? How do you see it in different areas of the world?
Yes, so this study that I mentioned actually went down that level of detail. So it had, I think it was 15% of Swedish energy being supplied by rooftop photovoltaics in 2050. So they actually went to the detail of how much would be field mounted and how much would be prosumer type systems. So that might include factories and things like that, as well as private homes. So Australia now, last year we generated 12% of our electricity, the total grid electricity, from photovoltaics, and the majority of that was on private homes. So it can really make a big impact. And you know, it was private citizens investing in those systems rather than the commercial you know, companies supplying that have traditionally supplied power to the grid.
Today it's about 1 terawatt installed in the world, and here is then the capacity in 2050. Where are the installations today, mostly?
Yes, let's just think. Well, China has led the world, like Europe led the world in market development to about 2010, and then you know, the German market was just getting saturated, in particular with photovoltaics, and a couple of countries like Spain and Italy had bad experiences because their feed-in tariff programs were sort of bottomless pit type schemes. So China took over responsibility for market development post 2010. So they, at the end of last year, had 234 gigawatts installed of that, you know, approximately 1 terawatt worldwide. So most solar is in China. In other countries of Asia, like Vietnam, really had a burst of activity the last couple of years. And the reason there was something that was mentioned before, the speed of installation. You know, they had this skyrocketing demand for energy, and they could just put the solar in, you know, 18 months from thinking about it to having the system working. And India, there have been big markets. Japan since Fukushima. And the US is a sleeping giant. It's sort of slowly growing, but periodically tariff actions there sort of make it a very stop-start uptake in the US, but it's sort of regarded as a sleeping giant. And then, of course, Africa is the long-term market. So for the US Sustainable Development Goal of universal access to energy by 2030, photovoltaics, either as home systems or as mini grids or through grid electrification with grids that are increasingly solarized. Solar is going to play a big part. If that goal is met, solar will play a big part in meeting it.
My name is Maria Köhler. Could you please comment on the dismantling of solar cells and the handling of the waste?
Yeah, so that's becoming a very important question. So, the amount of waste isn't enormous. So one of my colleagues did a calculation. If we powered all the world primary industry like this with solar, how much extra, most of the module is glass, how much extra glass waste would you generate? And the figure they came up with is 40% of the present glass waste stream if you supplied all primary energy with photovoltaics. So although you'd rather not have that 40% added, it's not like it's adding 40 times to the amount of waste. It's compared to the waste you get, say, from fly ash, from coal plant and so on, it's a very small amount. But increasingly the industry is concerned about taking responsibility for recycling. And in Europe, I think it's already compulsory that you recycle the waste at end of life. I visited a factory in France just last year that actually is set up to do that recycling, and it's recycling all the French waste as it gets generated. So I think that's the type of thing that'll happen worldwide. So there's not a lot of waste getting generated now, but further down the track with these enormous quantities, particularly with the IPCC and the International Energy Agency calling for rapid, immediate installation of solar as the best strategy for getting us on the right path to addressing climate change. There's going to be a lot. That exponential growth will hopefully continue and will be generating a lot of waste, increasing amounts over that increasing number of installations over years, that 20 or 30 years down the track will be waste. So it's being taken very seriously by the industry. Unfortunately, there's not much demand for recycled glass, so that it's not going to be a profit making exercise recycling solar panels. There's a bit of silver in there, but it's hard to get at. So the main product, the aluminium frames are easy to recycle, and that's already done. But the glass is just sort of more glass waste, and not a huge market for it. So the cost will be built in at the point of sale. The manufacturers will have to assume the cost for the final disposal in their selling price, is the way things will work out.
I think we have time for one more question. Yes, Elisabeth?
My name is Elisabeth Ratte, and I am thinking a little bit about the output, this low voltage DC. Now, how much of development is it so that one could use the low voltage directly, for example, in houses where you have this on the roof, or is there a development there so that you won't have all the losses due to the commercial?
Yeah, so I probably didn't explain it too well, but within those solar modules I showed, each of the cells is connected in series with an adjacent cell. So typically there's 60 or 70 cells within a module, and that their voltages just add. So you're dealing with 60 or, well, you get about 0.6 of a volt from a silicon cell when it's generating its most power. So you're getting like 36 volts out of a 60 cell module. So you're getting quite a reasonable voltage there. And then in the field, the modules are generally connected in series with each other. And a lot of fields now operating at 1,500 volts. But you can do things like, 1 volt is a little bit low to convert efficiently to a higher voltage, but a 36 volt module can be converted to, 240 volts, either DC or alternating current quite easily. And the electronics for doing that are quite efficient, and there are companies that are profitably marketing electronic gear for doing that for modules now. So, handling 1 volt, converting that to a different voltage you can't do that all that efficiently, but get up to 30 volts and it's quite simple to do with standard technology, and the costs aren't exorbitant for doing that now. there's probably more, people would like to go to higher and higher voltages, for these big field installations, and so probably go to 3,000 volts as the next, because that just reduces, like you suggested, it reduces the losses associated with working at low voltages. So, in the past it was 1,000 volts, it's gone up to 1,500, but 3,000 is probably feasible in the longer term.
Okay, so thank you very much. I think we have to stop there, but you will be available during the lunch also if people have more questions. So
Could I
thank you
have
very
one?
much. And now we go to the last, but not the least, speech of today. And that will be given by Elmqvist from Energiforsk. And the title is Different Energy Sources and Their Integration in the Future Energy System. Åsa has a background within wind energy and has worked with energy research coordination for more than 20 years. She is now responsible for the area Energy Systems and Markets at Energiforsk, which is a research institute here in Stockholm, and was the lead author of a recent report on power production costs. So we are very much looking forward to your presentation. So please, Åsa.
Thank you, Göran. So, thank you for welcoming me here. And I will give you some insights from the report that you mentioned, and combined with some other knowledge that we have gained within projects performed at Energiforsk. And as you said, Energiforsk is a research company or an institute, and we are owned by the Swedish energy business through their branch organization Swed Energy, and also Svenska Kraftnät, the Swedish TSO, is one of those are the biggest owners. And what we do is that we gather questions from the industry, and we find the best researchers to answer them, and we coordinate the performance quality, make sure it is made by enough quality, and then we communicate back the knowledge and the information to the industry and make sure it is used in a good manner. So it's very much close to the means and what we are here for. So to make academic knowledge used actually out there in industry and in policy. So my approach to this question that I got here is that I would like to start with looking a little bit into the future energy demand. We have touched upon it already, but I will give some other aspects, and of course focus on electricity. And then we will link this to the production scenarios that we have made within our projects. And what would the likely energy mixes be in the future scenarios if you count on the cost optimization to be the winning team? So that's how the models work. And then we want to ask what would be the additional costs to these production costs, like system costs, which is one of the important questions when you want to look at the integration. What is effects that will end up with someone else than the owner or the investor? So we have tried to look at that a bit, and we have tried to quantify them, and I will get back to how well we succeeded in that. And the approach we have is Swedish mainly, but of course everything is interlinked, so we need to put the Swedish system in the Nordic and also in a European context. And everything we do here is with the basis that we have fossil-free ambitions and carbon-neutral solutions. The report that I project managed, it's called Electricity from New Power Sources, and is a cost study. The instruction for the project was to create a base for analysis and discussion about costs for new power generation. And it is important that it is the base for discussion. It's not necessarily the absolute numbers that are the answer to what does new electricity production cost, but we want a more informed discussion about this. And we started with the situation for investments in 2019 and 20, and we wanted the actual figures and information for those years. So it's not really a forecast, but what are the costs by now when we carried out the study. The base approach was the LCOE. I don't know if you are familiar with this concept. It's the levelized cost of energy. It is when you put together all the costs, the investment costs and the operation and maintenance costs and some reinvestments that are made through the lifespan of a facility, and then you divide those by all the hours this facility produces or is expected to produce. So you will receive an average cost per energy, for instance, per kilowatt hour. And when we started out, we wanted actual figures from real investments made in Sweden by this time, and we quite soon realized that it was almost only land-based wind and large-scale solar that we had these figures from. So for those, we have made interviews and we received calculations, real investment calculations. So we had to do this NDAs and so on. But for the other power generation sources, we have made assumptions with the help of some experts, and we show all these assumptions. So we made the best guesses that we could for what would have been the cost if investments were made by this time. And we discuss a little bit about why are some investments taking place and why did other not take place. The results, in short, for the LCOE part of the study looks like this, where we have category A is those that we have what we call real numbers from real investments as sun and wind. And the others we call category B are those that include assumptions. And we also divided these in those that are dispatchable, which you can plan, and those that are dependent on weather on a short basis. You could argue that hydro is also dependent on weather, but we put those among the dispatchable power sources. And you can see that there is a great variety among some of those. For instance, the Villa System small-scale sun, here we received the information from the statistics that the Energy Agency gets when they deliver subsidies for those who invest in small-scale solar. And you can see that there is a great variety. Of course, this has to include a lot of assumptions, but they can take quite expensive parts, expensive investments, so they do not only invest in the lowest price. There are other initiatives and other incentives for buying solar small scale. And the reason for hydropower being so large is, in short, because it is very much connected to the projected revenue. If you can expect to get a lot back from your investment, for instance, if you can produce on hours with very high prices, then you can take a higher investment cost and a higher LCOE, and those investments can actually happen during certain circumstances. So we had this full span. when we did this, we wanted to include the actual circumstances that the investments were made under. So we included the real costs of capital for those diagrams you just saw. But some want to see what is happening if we add the same cost of capital to the different power sources. So therefore we did this sensitivity analysis to be able to make those comparisons. And for those of you who do not read Swedish very well and want to know why there is something below zero, it is waste incineration. So you can get money from burning your fuel. So if you have income from your fuel, then you can get negative cost if you have no cost of capital. So that's the reason for this. What we learned during this work is, of course, that the answer to what does new power generation cost is it depends, because there are so many co-varying parameters. So you really need to know, for instance, what price for money, what capital costs you can receive. Also, we saw that it's not really meaningful to do this by power source to power source, because we will need every cheap power that we can get. So it's not about putting wind towards nuclear or so. Rather, we need to address what is needed by the system, what abilities and requirements does the system have, because they are so different. They have different costs, but they have so different abilities and possibilities to contribute to the system. So it's more meaningful to discuss this. So a little about what we will need of the consumption. One big driver is, of course, the electrification of transport sector. And here we can see that it will be, by 2050, it will be a very big driver for the cars, but the trucks aren't very far behind. They are like 5 years behind. And altogether we will see a huge need for electricity from the transport sector. We have also talked about the hydrogen, and we see that when we just model for cost efficiency, hydrogen isn't taking very large roles in those scenarios. So for the least cost, you see the bars at the right, at the left. But when we add the ambitions by the EU and what industry states that they will need, we get severe amounts of electricity needed for producing hydrogen, as we have already touched upon today. So what does this mean for our countries up here in the north? If this is what we have today, and we start with the least cost scenarios and also the very high scenarios for adding hydrogen production, we see that we have quite a large challenge in front of us that we will have to cover by electricity, by new electricity. Coming back to this system costs, what we did within this scope of work for the cost report, we looked at what is a possible way to to calculate the add-ons, except that adds on to the LCOE, like a system value or a system cost. And one way to do this is to see what is the price on the spot market the hour this particular facility actually produces power. And then you can see an average, is this higher or lower than the average, and you will get some kind of a value factor, we call this. So this is one thing that is possible to do to calculate this system cost. So this we did for the relevant power production technologies that we see in the future in the Nordic context, and this is very interlinked to a study that is called Nordic Clean Energy Scenarios. So we took those LCOE figures and we added or took away a cost adder or a value factor for the different scenarios that we have had identified. And it's worth to mention that we do this as because we have really no standards available for this, for calculating system costs. We try to look at what international agencies has done. For instance, IEA, they have something they call value adjusted LCOE, and in the US there is something called levelized avoided cost of energy. But we saw that those components in those calculations is not really relevant for the Swedish market setup, because those much of those parts that are calculated in those add-ons are already included in the investor's costs. And I will show a little bit why here. Because you see the profile cost, as I described a little bit earlier on, this is actually something that comes on the investor or the owner as a benefit or a cost, depending on which hour the facility produces. And then you see the balancing cost, that you have the orange small square here. This is also something that is normally taken by the production owner, because you have to pay for imbalances. So this is not really something that you can add on as a system cost, as it would come on the system somewhere else. So it's included in their LCOE calculations. And also the grid costs is taken. Now we have some changes coming up for offshore wind, but up to when we did this report, all the facilities that are taken into operation, they have paid for their own grid connection costs. So it is also included in the LCOE and therefore cannot be added on. And this picture also shows a little square that takes the pillars down, that is flexibility, and this is something that will make this cheaper because of reasons we have also touched upon earlier, since we will not need, for instance, all those ancillary services so much if we can have a flexibility that takes care of some of those needs and the challenges that come with a more variable electricity production. This is most things I already said. It is the actual price, the hour you produced, and this is of course possible to forecast. So this is what we did. And you need a scenario to calculate this in, because it's not meaningful to calculate the profile cost if you do not have a variation of the others. You need to know when all the other production sources are in operation. For instance, if you have a large share of sun, you will of course have a large share of production during midday, and so on. So this is essential to have a scenario. A little more of what we did and what we did not do. These are Danish consultants, the EA Energy Analysis, that have done this for us. So they included the profile cost and the balancing cost in their calculations and the forecasts, and they excluded grid costs and ancillary services because we had no information that was relevant to include in these modelings. So the outcome that we have is an adder to the LCOE, or a saver if it is negative, for those specified technologies and for each of the price areas we have in Sweden. A few words about the model that we did this in to calculate the coming prices. It's an open source model, and it gives you production by every hour, hourly dispatch, and you see the power prices. And it also takes into account the transmission limitations and so. So it's a model for all Nordic countries. Jag har ingen klocka. Hur ligger vi till? Ha? Okay. So the scenarios that we landed from this Nordic Clean Energy Scenarios project, they look like this. They are two different for 2030 and 2050. In our report, we call these A and B because we didn't really want to put years into those. It's not important. It's the mixes that we wanted to address in the project for the cost study. So the results about these value factors is that the value is very dependent on the surroundings. Also that the variable renewable energy sources, they will have very much more negative value as they grow. And this is what we call a cannibalization effect, since everyone is producing more or less at the same time. For instance, when the wind is blowing or the sun is shining. If you have a large share of the same production, then you will, of course, receive a less share of the surplus over the average of the spot market price. And if you have dispatchable power, it is a high value because you can steer this to high price hours. So they are high valued over time. So the analysis of the whole project that we did is that we have sink-in costs for new electricity production. So we have quite good chances to get more production. Not to say that we get all the things that we need because we have a large demand, but it's quite promising that we can take a large share of this with cheap electricity. And when you want to do comparisons, you will really need to have a good picture of the assumptions that you have made. It is very important. So you cannot just pick a figure from a graph or something. You really need to ask questions about the assumptions made. And for investments, the costs is one part, but it is very much dependent on how you look at your future revenue patterns. Do you have a dispatchable power generation source, and do you count on getting extensive large revenue streams from ancillary services, for instance? If you count on that, you can take a higher share of a cost, of course. So we focused on costs, but it is, of course, interlinked with possible income. And for the future and for the integration, it is very crucial to know what energy mix will we have and how much flexibility will there be. This is very crucial for what the costs for integration will be and how smooth integration will come. And the scenarios, of course, have very unknown parameters, so you really need to stipulate those. And you will always receive arguments that those are wrong, but you can just be sure that scenarios are probably wrong, but it's a basis for discussion. And whether the auxiliary services are financed by the system, like the government or so, it may be possible to count them as a system cost, but if it is a market that is regulated by itself and it's taken care of by the production owners, then it's probably not suitable to see those as a system cost, because it will end up by the electricity producer, if you have a market as we have in Sweden today. So those were my messages that I wanted to send to you from our work. Thank you.
Questions here too, but first I would like to make just a few remarks. You said in the beginning, and I think that's very important, that these are not absolute values, but as you're using the same method for all these studies, comparisons can be made. So it's to evaluate different options, but the absolute numbers we should take with a grain of salt.
Exactly so.
Yeah, you said that, but I want to
it's very important.
Because people are quite often just taking the numbers and say that are the absolute numbers, but that is not.
Mm.
And also, it's very interesting, this system integration study you have done in the report. You should be commended for that. And this report can be downloaded. If you go to Energiforsk homepage, you can download it there. And it's very good reading. And congratulations to an excellent work.
Thank you. Also, the sub-reports from the experts, they are also downloadable from there, if you want.
Okay, so questions? Yes, please. Yes, Elisabeth.
I wanted to ask you how this compares with Svensk Näringslivs rapportering, which is about very similar results, which is this kraftsamling. Because there they have done many modeling, what the cost will be for different electricity systems, depending on what are the components of them. And this report is a year or two old now. How does it compare with your work?
We haven't made actual comparisons, because it turned out to be there are other cost studies as well, and we see that it is a matter of how to frame your facility. For instance, we have examples when we started these interviews to see what were the actual figures for investments. You see that someone had to build a harbor to support the infrastructure. Someone had to do something else. If you have a green field, and a lot of investors, they start with a facility that it was already, to some extent, already there. So it's very hard to do those comparisons, and that's why, as Göran said, it's more meaningful to do the same setup and make comparisons with the same framework. So we focused on that and did not really focus on actual costs and what were the actual costs from another study, because it's very hard to do those comparisons. The answer is it depends.
More questions? Yes.
One basic factor I want to ask, the offshore needs sea cable. Is that included in your figure? The individual sea cable to get the power on shore?
Yeah, it is included here that they took the costs in the LCOE. Those consultants that made those studies, they included it. By the time we performed this, it was just about the discussion initiated about taking away the costs for the cable to a point offshore. But by this time, they had to take those costs, and those are quite probably one of the reasons for the investments not being done by this time. We didn't have any actual investments in offshore wind during our study, and that is one of the reasons probably. Yeah, it is.
Thank you very much for the presentation. I unfortunately missed a bit in the beginning. I had to take a call, but have you taken into consideration the costs for relating to the question before of the permit processes and bureaucracy?
Yeah.
And,
Yeah. All the project costs and owners' costs, they are included in the LCOE figure. And for wind and large-scale sun, I can say that they are real costs, what they actually were for those. Yeah.
And not only the factor costs, not only the nominal costs, but the factor costs of delays and so on.
Yeah, contingencies we have, they do calculate with those as well. Yeah, included. And you can read the details about it in the report. We have explained it quite thoroughly.
Any more questions? Yes, Hans?
I have filed a question to you and to Göran, and rightly as you say, it's better to have the different costs individual, because at the end it's all needed. And this in the political discussion ends up contrary to nuclear, because once you come to that, they say it takes too long time. And as the nuclear is pre-decided to certain areas, I claim that you should type acceptance for Ringhals, for Oskarshamn och Simpevarp, and for Forsmark. These are the sites, and all the acceptance because of sites should be given beforehand. Then you have only the time for delivery to compete on. What do you say to that?
I say that we again tried to find the actual calculations that the possible investors for nuclear in Sweden had on their table by this time, and they had exactly these discussions that you mentioned. And we have very extensive discussions about if we should include the extremities of building times or not, if we should. But they said this is not what we calculate on. We calculate on some average. So we were quite, criticized for taking a smaller span of costs for nuclear. But we had the discussion with these experts, and they also really have insight in the cases, and we explained it also in the report. So I say we.
You have a very important task there.
Yeah. Yes.
Yeah. So, well, I think there are any more questions. So once more, I encourage you, if you're interested in this area, to download the report. Have a good time. Thank you very much, Åsa, for your presentation. Okay, so we have come to an end, and I would like to make two remarks. First one is, so we have come to the end of a very interesting morning here, and I would like to make two remarks. One, I was actually triggered by your map of the Balmoral system, where you saw Europe. And the thing is that it has not been very much noticed in the press, is that in the beginning of March, actually the Ukrainian power system was synchronized to the European grid. It used to be synchronized with Russia, and it should be synchronized with the rest of Europe in 2023. But they actually forced that plan, and they did it then during the first weeks, and that was really an engineering achievement, I think, that they forced these plans, and so Ukraine is now connected to the European grid. Okay, that was a small remark, and I would like to remind you then that this was the first seminar in this series, and in a couple of weeks there will be the second one on energy storage, the 8th of June, and there we will also have three speakers. It will start off with Willem de Hesseler, who is a professor at KU Leuven in Belgium. He will talk about the role of storage in future energy systems. Then Thomas Schmidt, who is with ETH BSI in Switzerland, will talk about power to X, power to gas, and other technologies. And then finally, Christina Edström from Uppsala University will talk about future battery technologies. So I hope that I have teased your appetite for this, and you will, if you not already have, sign up for that seminar. So with that, I would like, of course, to thank all the speakers here today. Very interesting presentations, and you will be available, at least two of you, during the lunch out here. So if you have more questions, there will be opportunity to do that. And I would like to thank everyone for coming here, and I hope that you have had as much out of this as I had this morning. So thank you very much for coming, and I hope to see you then in a couple of weeks again. Thank you.